Hey guys, we're three guys. I'm Ryan,
I'm Kai.
I'm Brody.
and today we're going to talk about the electrical properties of our semiconductors and metals. First, we're going to talk about the electronic configurations. This is the arrangement of electrons in orbitals around the nucleus. On the right, we have the periodic table, and on the left, we have the flow at which the electrons go through the orbitals. The first one we're going to talk about is copper. It is 29 electrons, and it goes through the 1s, 2s, 2p, 3s, 3p, 4s, and the 3d orbitals. As you can see, it would originally go through only 3d9, but 3d10 is more stable. Therefore, we have it as 4s1, 3d10. And to simplify it, you can say it starts at argon, 4s1, 3d10. Next, we have titanium. Titanium has 22 electrons, and it goes through the 1s, 2s, 2p, 3s, 3p, 4s, and some of the 3d. The amount of the 3d is 2. It can also be expressed as argon 4s2, 3d2. Next, we have lead. Lead has 82 electrons, so it's going to go through all of them, all the way until we reach the 6p orbital. And it goes 6p2. Next, we have tellurium. Tellurium, as we can see, has 52 electrons, so it's not as much as before, but still goes through all of these orbitals until we get to the 5p orbital. And it goes 4 electrons into the 5p orbital. Next, we'll talk about the semiconductor band gaps. For lead, it's very small, since lead is basically a metal and doesn't really have a very visible band gap to begin with. So its band gap is 0.2 electron volts, and it therefore has a high conductivity. Tellurium is also very small. It's a little bigger. It's at 0.35 electron volts. It also has a high conductivity. Now we're going to talk about the p-type doping options for lead and tellurium. So p-type doping is when the doping element has less valence electrons than the overall semiconductor. So for lead, this would be anything with 3 or less valence electrons, since lead has 4 valence electrons. So some examples would be boron, aluminum, and indium. For tellurium, it would be anything with 5 or less valence electrons, since tellurium has 6 valence electrons. This could be nitrogen, silicon, or germanium. Now, we're going to talk about the n-type doping options. As you can guess, this is opposite to p-type, so it's anything with more valence electrons. As we look at this picture here, we can see that it is when there are excess electrons with the doping element. So for lead, this would be anything with 5 or more valence electrons, like phosphorus, sulfur, bismuth. And for tellurium, this would be anything with 6 or more valence electrons, chlorine, iodine, fluoride, etc.
Next, we will find the concentrations for our semiconductors. As you can see on the right here is a formula for the concentrations inside our semiconductors. See, it's in terms of sigma, which is our conductivity. Our E is our charge of the electron, and mu E plus mu H are our mobilities for our electron and the mobilities of our holes. We found here that lead has a concentration of 10 to the 16th per cubic meter, and tellurium has a concentration of 10 to the 25th per cubic meter. Next, we have our mobilities. As we see here on the right, our mobilities can be found using the following equation. Mu, which is our mobilities, is equal to the drift velocity divided by the electric field. On the left, we found our electron mobility for lead to be 1.6 meters squared per volt seconds. And for tellurium, we found our electron mobility to be 1.3 meters squared per volt seconds. For our hole mobility, we found lead to be 0.2 meters squared per volt seconds. And for tellurium, we found it to be 0.13 meters squared per volt seconds. Next, we have our electrical conductivity. To find our electrical conductivity, we want to use the equation on the right. The equation on the right is in terms of our concentration, our charge of our electrons, and our mobilities for both the electron and the mobilities for the hole. So we found for the conductivity of lead using the following equation and the results that we calculated earlier in the presentation, we found our conductivity to be 2.88 times 10 to the negative 3 Siemens per meter. For the conductivity of tellurium, we found using the same equation and the results that we calculated earlier in the slideshow, we found that to be 2.88 times 10 to the 6 Siemens per meter.
Next, we're going to talk about the applications of lead tellurium. Lead tellurium has a narrow band gap, which makes it useful for infrared sensitive solar cells. We researched and saw that an N-type lead tellurium monolayer found that it makes for a wide band gap with low thermal conductivity. The lead tellurium monolayer is suitable for thermoelectric applications. We found that lead tellurium is chemically stable, so its main use is for its durability. It also has a high heat transfer, and it is only limited to its toxicity. We're next going to talk about the specifics in its application in electronics. Its high thermoelectric efficiency makes it ideal for converting heat into electricity. Used for power generation and cooling applicants, and its narrow band gap once again makes it sensitive to infrared radiation. Now for its application in LEDs and photovoltaics. It is used for light-emitting diodes. These LEDs are used in the medical field, gas sensing, and optical communication. Before explored for photovoltaics and as an absorbed material in solar cells. Its narrow band gap and ability to absorb infrared light makes it suitable for improving the efficiency for solar energy systems by utilizing the infrared portion of sunlight.